thank you so much, Alex, Michael, for inviting me. It's really a great pleasure to talk about black hole physics. I'm going to disappoint most of you by not talking about the things I don't know, which are, ray tracing and images of black holes. But I will make contact with what I think is the most amazing features of BECS and other observatories to understand black holes. So my purpose is very simple. I would like to just talk for a few minutes about what we know about black holes in the era of gravitational wave astronomy and how that relates to the things that BECS and other telescopes want to understand. And I think it's never too much to stress that black holes are unique objects in the universe. And in fact, as Chandrasekhar once said there, it's really a shattering experience to understand that a single mathematical expression, this Kerr geometry, describes an untold number of black holes out there in the universe. It's kind of a gift that general relativity gave us, that any black hole spacetime in vacuum should be described by two parameters alone, and that's the black hole mass m and the black hole spin a in geometrical units, where I set the Newton's constant and the speed of light to 1. Now, this property comes in hand with another one, which is a consequence of singularity theorems by Penrose and others, which is in the interior of each of these untold number of black holes, our knowledge of general relativity or our knowledge of gravity breaks down, right? There are singularities, things go berserk, and therefore I think this provides really an extreme motivation to study the near horizon geometry of compact objects. Now I'm going to use this a little bit, so let me draw a cartoon of a black hole spacetime. So I'm taking an equatorial slice. I like to do this because it looks simple. So if I take an equatorial slice of a black hole spacetime, I'm going to see, of course, the horizon. It's a surface from which nothing comes out. And I think it's always good to remember that black holes are black. So there's no evidence that we can ever give about the existence of black holes. We can get close to, but we can never say with certainty, with finite time observations, that we are seeing horizons. This cannot be done by definition. But as we move outwards, there's interesting features which are very, very special to relativistic theories of gravity. One of them is the existence of ergo regions, right? Once your spacetime is rotating, there's a static limit beyond which nothing can remain at rest with respect to distant stars. So if I take a spaceship, a powerful spaceship, and I turn my engines on, even then, if I'm inside the ergo region, I cannot remain at rest with respect to distant stars. And I think Elliot already talked a little bit about the consequences of this. I like to give very, very simple examples, and one of them was provided by Penrose. I can use this region to extract energy, and the simple thought experiment goes as follows. I construct a circular metal ring to which I attach two shafts which are glued onto a magnet. I lower this construction onto the ergo region. By definition, the ring has to co-rotate with the space-time. Hence, by Faraday induction law, I'm going to extract energy away from the system. It's a really, really naive way of showing that we can extract energy from rotating black holes. It doesn't look like much, because we can do this with any rotating system on Earth, right? We just take a carousel, we can lower the exact same system. The difference is we're lowering this device onto vacuum, right? So we are actually extracting energy away from vacuum. So I'm not going to say more about this, but it's really a thought experiment with far-reaching consequences. If you look at that equatorial slicing of your spacetime, there's a final region, which I find very, very interesting and on which I'm going to focus for the rest of my talk, which is the light ring. I'm sure all of you know much more than me about the light ring, but let me tell you the few things we should always bear in mind. It's a closed light-like trajectory, so I can shine a laser beam, a high frequency beam here, and it's going to orbit on a closed trajectory. This is a non-spinning black hole for now. You can do this also for spinning black holes. There's an interesting structure. But if you focus on black holes with no spin, then you can work out the properties of this light ring. And distant observers will see a frequency for photons on this light ring, which goes like 1 over 3 square root of 3m. But they will also see that it's unstable. A photon on this orbit wants to either go down the horizon of the black hole or go off to infinity. And the time scale is given by this so-called Lyapunov exponent, which is also 1 over 3 square root of 3m. Right, so it's an unstable motion for high frequency components. But I think it's important to bear in mind that this is, if it happens for high frequency radiation, you can also understand most of the dynamical properties of black holes in terms of this. The light ring traps radiation, it traps it for a finite amount of time, and this explains the late time behavior of black holes, as I'm going to tell you in a minute. For example, if you let a star fall onto a black hole, and I'm doing this in exactly this plot over here, it's a homogeneous source of light. It's falling radially onto a Schwarzschild black hole. So I'm measuring the total integrated flux at large distances over the flux within the source frame, okay? As a function of time. And what you can see is that the flux roughly is a constant at early times. I need to start the star falling somewhere. But then at late times, the flux falls off as the exponential of minus t over 3 square root of 3m. And this is very interesting because what's happening is that the star is radiating in all directions, okay? Light rays that go almost on a radial trajectory reach the observer, but at late times, because the star is also shining onto the light ring and the light ring traps radiation, what you actually see at late times is not light from the star itself, but light that's being recycled by the light ring. So the light ring has this amazing property that it's the last dying tones of a black hole. They are kept in the light ring. Okay, and so the properties of this radiation really are due to the light ring. This work, by the way, was started by Polyretz and Hames and Thorne many, many years ago, and recently was just worked out for this particular case of a homogeneous star. Okay, now this is high frequency radiation. Let me talk about my subject, which is black hole spectroscopy. And now I'm talking about radiation fields, waves at any given frequency. Now, the way we have to understand black holes, dynamical black holes, that are the end result, say, of a coalescence of two neutron stars or two black holes, is to actually think backwards in time. If we think about the uniqueness theorem, the gift of general relativity, the end state should be a Kerr black hole. So if I think about going backwards in time, then at this point over here, I should be looking at a slightly disturbed Kerr spacetime. So I can expand the field equations around a single distorted Kerr black hole. If you do this exercise, you'll realize quickly or not so quickly that all the metric fluctuations can be combined into a single master function that I call psi that obeys to linear order. So I'm expanding all quantities at linear order, obey this very simple partial differential equation. And you can, well, it's so simple that you can actually ask this looks like an oscillator. What are the proper modes of oscillation of this system? So you Fourier decompose your equation and you ask what characteristic frequencies omega satisfy the physical boundary conditions of my problem. You'll realize quickly that you need to solve the problem numerically, and you'll also realize that the impact of those frequencies in the time domain response is such that your signal, your gravitational wave signal at late times, has this form. It's an exponentially damped sinusoid where this timescale tau and frequency f are really just the characteristic modes omega. Okay, we know how to calculate these numbers with 20 decimal places, and we also know how they behave at any given angular number L. Let me just point out that when you do the exercise of massaging the Einstein field equations into this single partial differential equation, you did away with the angular dependence by expanding in spherical harmonics. Hence, your results always depend on angular numbers L, M, the azimuthal dependence, and some overtone M. Now, it turns out, maybe not so magically, that when the angular numbers N, L, and M are very large, meaning your wave has a very high frequency, then the characteristic frequencies in this WKB limit actually reduce to what we just saw about photon motion. They have a real part which is dictated by the frequency around the light ring, and an imaginary part that describes the damping of radiation, and that's controlled by the Lyapunov exponent. It's a beautiful correspondence that relates gravitational wave finite frequency observables to light ring properties, to null geodesic motion. It's really a beautiful way of thinking about how black holes relax. And that's something that Bex is going to do for us once we find sufficient and strong evidence for the existence of light rings out there in the universe. Now, if you actually want numbers, I've done that for you. So I'm plugging here on the y-axis the imaginary part, on the real axis the real part of these frequencies. You see, if you as you go up in the y-axis, the mode becomes more and more irrelevant because the time scale of the mode becomes shorter and shorter. It quickly dissipates away. And the fundamental mode has a frequency of order 1 kilohertz for a 10 solar mass black hole, and a time scale of order 0.5 millisecond for the same black hole. You'll quickly realize that black holes are terrible oscillators. The light ring is a terrible oscillator. The quality factors are of order 3. They don't actually ring. They just, they relax with the thought. They quickly get away. They quickly damp out anything that you put in there. Okay? It's both a problem, because to actually dig this stuff out from data is messy, but it's also kind of a gift. Black holes are stable partly because of this. So I think I still have a few minutes. Let me tell you how we actually use this. And the fundamental questions that I think we all want to answer is, are we really looking at black holes? And can I find evidence that light rings exist in the universe? And are these the curved black holes that GR predicts? So we call this black hole spectroscopy if we're just looking at the final relaxation stage of these compact objects. Now you should ask, that's all beautiful, but how do we actually excite these modes? Well, you excite black holes with anything that you want and that you can. For example, if you have an accreting spacetime, like this spacetime over here, you have a thin accretion disk or a puffed out disk accreting onto the black hole, of course you're exciting the black hole in the same way that the sun is always being excited by nuclear reactions. And in fact, if you look at the gravitational wave signal from accreting black holes, you see there very clear signs of excitation of the light ring modes. The problem is that the amplitude of these signals are really weak. If we want to have a hope of seeing this, we really need violent, powerful events in the universe, and these really are provided by almost equal mass black hole mergers. Okay, so if you take two black holes, you coalesce them, then the signal is going to look something like this in the bottom lower right. This is a typical gravitational wave signal. This is what LIGO saw. In fact, the very first event that LIGO saw looked something like this, and we can do spectroscopy. The idea is very simple. We fit the late time gravitational wave signal to a simple exponentially damped sinusoid. We know the parameters to 20-digit precision, right? So we can do this. Now, of course, the first problem you're going to face is, when do we fit? Clearly, at early times, I'm not talking about a single distorted black hole, so I should do the fitting at late times. So LIGO did this for us. The black solid line is the 90% posterior distribution for what you'd expect for the decay timescale and frequency if you just look at the low frequency component and you infer the final black hole properties. The real spectroscopy where you're feeding to exponentially damped sinusoids are shown in color. For instance, the green curve fits to an exponentially damped sinusoid 1 millisecond after the peak, the purple 3 milliseconds, and so on and so forth. You see that the errors are big, but they all contain what you'd expect. They all contain the low frequency expectation, okay? I think for most of us, this looks like, yeah, it's okay, but you need to bear in mind, this is the first ever observation of a black hole binary, the first ever spectroscopy test of the black hole nature of what we have there. This was 2016. 2 years ago, I asked a postdoc, Vitor Cardoso, to project where the field was going by imagining that we have ring down a black hole relaxing with a signal to noise ratio of 40. Okay, the first event had a signal to noise ratio of around 7. This is what you get. First of all, you measure not only one mode, the dominant quadrupolar mode, but you measure two modes, and the error bar is so much smaller with signal to noise ratios of 40. Okay? Now, LISA, for instance, is going to fly 10 years from now, and it's going to see this similar events with signal to noise ratios of thousands. This is where the field is going. We're going to be measuring not 1 or 2, but 10 different modes with, I can't even plot the error bars for LISA. This is where the real test of the black hole nature, the real test of general relativity is going to happen. The future is now, in fact, an event very similar to what I had asked Gregorio to project, was seen a few months ago by the LIGO collaboration, okay? So signal to noise ratios total of roughly 70, I would say of order 40 or 30 in the ring down, and we do see evidence for 3 modes already. It's a beautiful, beautiful direction. This is 2025. 10 years from now, you're gonna be seeing a lot more of this, guys. I don't want to bother you with this, but it's important to know that what BECS and other telescopes can do for us is to do complementary information to what gravitational wave signals can do, right? In a gravitational wave signal, we have access to the full thing, to the full enchilada of a dynamical space-time. BECS is a very, I would say, wonderful way of capturing a silent black hole and having a very robust way of extracting light ring properties. We shouldn't think about competing. I think we should think about complementing the evidence for this really amazing predictions of general relativity. There's a lot of challenges in understanding how black holes relax. We need to understand the environments. We need to understand the nonlinearities of general relativity. I just talked about the linearization procedure. There's so much more that comes into play. We also need to understand resonant excitation of modes. Let me tell you before I finish, I hope I still have a couple of minutes, but I'll shout out if I don't.
Yeah, no, you're good.
Let me tell you about things that we just started to understand may be important. And one of the things that LIGO is starting to get evidence for is of the existence of triple systems. Supermassive black holes surrounded by orbiting stellar mass binaries. For instance, this system over here, a supermassive black hole here surrounded by a binary that's orbiting. There's some evidence that some of the LIGO events may be coming from sources like this. Okay? Now, this stellar mass binary is evolving in time, so the frequency of the binary is evolving, and it's a wonderful kind of tuning fork, right? Because it's sweeping across the frequency, so you may think at some point it's going to excite the light ring of the black hole. It's going to hit frequency, it's going to coincide with exactly the frequency of the light ring of the supermassive black hole. So it's kind of a very intriguing prospect to have resonant excitation of light rings out there in the universe. The system is also cool because you can see everything. So we solve this from first principles. Solve means we solve for the motion of the binary and for the gravitational wave emission. And you see, I think for the first time, Doppler shifts, blue shift, red shift, beaming of radiation from first principles. In the middle panel, I'm showing you the gravitational wave signal plotted against a Giotto ray trace image of a star around the black hole. They really coincide. All the features are there, except that here we work from first principles. We have evidence, and that's something that we're exploring with Alex, that we can excite resonantly the modes of the black holes. I think you're going to see a lot more coming in the next few years. How do we map the location of the modes? Where exactly and how do we resonantly excite the different modes of black holes? It's an open question. I think it's a foundational question that we need to understand how we're going to answer. I'm going to finish by saying I promised that we would know about testing the Kerr nature, but we should also be able to say, can we know that this is a black hole? How do we know that this is a black hole if the horizon is lost to us? It's out there at infinitely far away from us. But you can twist the question around, right? If the excitation of the light ring is what gravitational wave observatories give us, take for instance this star, this red dot, thrown onto a black hole. When it crosses the light ring, this vertical line over here, it excites ring down. Book, there you go, a burst of radiation. This is the star crossing the light ring. If it's a black hole spacetime we're talking about, that's the end of it. A burst of radiation comes to the detector, another burst goes in, and it's lost forever because there's an horizon there. Now, if your object is actually not a black hole, it has to have structure somewhere. So the burst of radiation that you generated and went inwards at some point needs to interact with your object and needs to bounce back and reach your detector. So you see, you have, I would say, an amazing way of using observations to constrain the nature of your object. What you'll be seeing is exactly what LIGO saw, but if you wait long enough, you're going to see echoes, repetitions of the initial burst. The time delay between those repetitions should tell you where exactly the structure is, okay? And the decay time scale is going to give you information about the material that makes up these objects. LIGO is now using these insights to search for these objects. We haven't seen any evidence for late time echoes, and this constrains already some of the properties of these guys. So to conclude, black hole spectroscopy has begun. Really, it's a new era. It's even hard to think about this because we didn't have anything like this. We didn't even know how to think about these issues, 9 years ago. We're dissecting now every part of the signal. We need to understand the role of environments. We need to understand the role of nonlinearities. There's been a huge progress. The community didn't even exist 10 years ago. So, it's the new PhD students and postdocs that are learning how to speak a language that's being developed as we go. There's been a very thorough community review just a few months ago. And I guess my final point is absolutely we need to make a contact point between gravitational wave observations and imaging and light ring observations from telescopes. It's an absolute must if we are to convince ourselves that light rings and monsters such as black holes exist out there in the universe. So thank you so much.
Thank you, Vitor, for a very inspiring talk. And yeah, I think it's really remarkable that the detailed features of these gravitational wave signals with the time echoes and the damping of the amplitudes are controlled by the same quantities
Yes.
as those that control the photon ring images. I think we have time for one or maybe two questions. Marshall?
You didn't say anything about spin flips, which I think are a very interesting and, at least to me, fairly new feature of all of this, and something that I think could be very interesting if you could find a close black hole binary that something like Bex could observe, because I think those would happen
Yeah,
further away.
so you mean that we fine-tune the relative spin of black holes such that the merger flips?
Well, yeah, I mean, if you look at the numerical, the gravitational wave signals that they're coming out with, it's really weird how the spins can flip and that the periods
So
change and all sorts of things like that happen.
That's a wonderful thing that was born almost exclusively, but not only of numerical relativity. As far as relaxation of black holes are concerned, it's not really relevant because the final black hole is still going to relax in exactly the same way I described. We understand this process. We understand spin flips and that they leave a residue in the relative amplitude of each mode, but the modes themselves again depend only on the final state.
Well,
and
but
we know
during the merger stage, or even a little before the actual merger, it seems like that might cause orbital signatures that a Bex array could see if you could actually find such
you still need a lot
binary.
of fine-tuning. I think it's wonderful if Bex sees that, but there's a lot of fine-tuning required for spin flips. Yes.
And thank you, both of you. Michael, do you want to ask a final question, if it's okay with you, Vitor?
Yeah, I think it's a quick question. I mean, it's a great talk, very inspiring. It's clear that it's the same underlying physics across all these scales and scale invariant and so forth. But what I'm curious is whether or not you think that there's a framework in place that's natural to quantify results from Bex and LIGO and LISA all in the same language. I mean, this is conventionally done with like PPN, but that's very kind of ill-posed, or not ill, it's ill-suited for this type of problem. So does that exist, or how should we be thinking about connecting Bex to the other projects?
I think we can do it. I don't think it has been done. Certainly we cannot use the PN expansion or any sort of fixed background expansion that we've been used to discussing. But I think the argument which is something we had in the white paper of a year or two ago, the question of let's strengthen the evidence. What evidence can we provide for the existence of light ring with Bex? Or the statement of what evidence do I have with LIGO or LISA that there's a light ring in the space-time? These statements can be done, they can be asked. they can be answered. I think we should get together and find a way to strengthen the evidence when we bring these two measurements together. I think it can be done. It was not done to the best of my knowledge. No.
Well,
Got it.
there's still
Perfect.
plenty to do.
Yes.
All right.
Yeah.
So once again, thank you, Vitor, for a
Thank
great
you so
talk.
much.